involves something other than area of rectangles. So branch out, we'll look at some triangles, we'll look at some other sorts of angles and circles and things like that. Generally speaking, there are a lot of types of functions that we could need to optimize, but the variety where you're going to be given some information and have to come up with the function to be optimized, they're generally going to be related to either some basic structures like, revenue is cost times whatever, like your price times number of units sold or something basic like that, or something geometric where you can look at it or see it described, or trigonometric, slight variation on the geometric, some sort of figure drawn out where there's something we're trying to optimize. Again, the general premise of an optimization process is that we're trying to find a best value of some sort, usually maximum or minimum value of something. In this case, this is in your textbook, but I do want to go through this example because it's kind of cool. Maximize or minimize, in this case, we're going to try to maximize area, but there are a lot of constraints on that. So although overall I'm going to be writing a function whose output is area of a rectangle, that's the part we're maximizing here. So there still is a rectangle, area is length times width. There are some other constraints here that are geometric in nature related to the fact that it's inscribed in a right triangle. And there's not a whole lot of dimension information given here, but there's enough. We could find other sides of triangles, of the big overall triangle. We could determine angles because we've got two sides of a right triangle. So sines and cosines and tangents could help us find any angle we wanted, in fact, in this whole diagram. So the idea is we're going to try to write a function whose output is the quantity we're trying to maximize, so whose output is area of the rectangle here, but taking into account all the relationships between the parts of that rectangle, the length and width, and the restrictions of being in this triangle. So it's not necessarily easy just to set that up, but if we can write a function that has one independent variable, that somehow links us to find this area of a rectangle based on knowing one value, then we can use some basic calculus at that point in time. It's not going to be super complex like some of the things you saw in your mastery, but using derivatives we can find when we've hit maximums or minimums. In this case we'd be looking for a maximum of an area function if it has a pattern where the derivative changes from increasing to pause to decrease, or going over the top of the hill. So positive derivative, then 0, then negative would indicate that we've found a maximal value. So in any case, looking at this diagram, there's a lot of different relationships. So I'm going to draw some things into this, but this is supposed to be a right triangle. And let's see, with a rectangle inscribed in it. So all of these places where I'm putting little tiny blue dots are right angles. There's the right angle of the main triangle, also of this triangle that's smaller. And since this is a rectangle that's inscribed, it's going to have right angles within it. And since it's perpendicular to the hypotenuse, those other angles outside here are also right angles. So notice we've got 3 smaller right triangles all in this large triangle ABC. So this is in section 7.3 in your textbook, so maybe this looks familiar, but I just want to point out some things along the way in case you either didn't look at it, got lost, or forgot, said, oh yeah, that made sense, but I haven't looked at it in a little while. So the main idea is I want to find something where I can find the area of this rectangle. So I'm going to use the letters that your book does, so which calls this length S1 and this length S2, the two sides of the rectangle. And so what I'd like to be able to do is write a function with one independent variable for area of this rectangle, which right now is S1 times S2. That's not something I can do too much with, but S1 and S2 are related to one another because of the triangle that they're in. We could also talk about them being related to components of the triangle as it is, like a particular angle. If you wanted to involve some trigonometry, there's multiple ways to solve this problem. But if you try with trigonometry, it ends up canceling itself out in the end, as does anything else. A lot of this will all reduce out in the end once we get together a function, because all of the pieces here are related. So thinking about just overall this triangle with things drawn into it. So I've got 3 right triangles inside another right triangle. Each one of those, well, especially this one at the tip is easier to see, and this one here, they share one of the triangle's non-right angles in addition to having a right angle. So if think back to high school geometry, these two at least very easily can say, oh, well, this triangle here has a right angle and the same angle A that the big triangle does. So it's got all 3 of the same angles. They're similar triangles, meaning the sides lengths are in the same proportion in this small triangle here as in the whole thing. Same with this upper one here. It shares the same angle C that the whole large triangle ABC has, as well as having a right angle. So this must be the equivalent of angle A. And again, the sides are in proportion. This one's maybe harder to see because you have to use other facts like, oh, well, this is intersecting at a right angle there. This is a straight line. That's a 90-degree angle. So whatever this is, the equivalent of angle C, I don't want to put a dot there because it's not the same size, the equivalent of angle C and 90 degrees and something else make 180. Well, then this must be the equivalent of angle A because 90 and angle C and angle A add up to 180 degrees, triangle rules. So these two aren't the same as one another, but this one is the same as angle C, and this one is the same as angle A. I don't want to get into all the little geometry marks here, but each of these 3 smaller triangles is similar to the overall large triangle that we've got. So that means their side lengths are in proportion to one another, and although I don't have any side lengths of these little triangles, I have side lengths for the big triangle. In fact, I have 2 out of 3 sides, which means because of Pythagorean theorem, right triangle stuff, I actually know the length of all 3 sides of the big triangle, although the hypotenuse isn't a rational number. Let me just write this side in a different color. This hypotenuse length would be, square root of 11 squared plus 16 squared. So if I need to refer to it, I can call it that. Or that's what, 256, 377, square root of 377. I don't want to approximate it, so I'll just leave it as one of those. But the length of that hypotenuse in the large overall triangle, not just the length of that side of the rectangle, that would be nice if we do that, but the length of the hypotenuse in this overall triangle would be this, assuming I added correctly, 256 and 121, yeah, 377. Would be the length of the hypotenuse, square root of 377, that is. So in terms of this, let me just start down here, starting with side 1. Side 1 and this side here, they meet in a right angle. So side 1 is across from angle A, so it must be similar to this side 11 that's across from angle A in this scaled down triangle. And, well, you can set up lots of different proportions, but I was checking earlier when I turned this off, which ones did they set up first? So in terms of looking at side 1, how I can express it in terms of other things in this diagram, well, I know side 1's related to this 11-inch side because it's across from angle A just like the 11-inch side is. And well, if I'm ever going to get to this side 2, I'm going to need something else. I'm just going to pick a second side of this little triangle here. I'm going to use the hypotenuse. I'll call it x, because x is short to right. That should be equivalent to this square root of 377. Not equivalent to it, but proportional scaled down version of it. So writing our proportion, S1 is equivalent, or is scaled down version of 11. So S1 is to 11 as side x, the hypotenuse of this little triangle, is to root 377. And again, there's however many different combinations of ways you could write proportions here. But this relates side 1 and a second side of that triangle, the hypotenuse, or relates measurements in the triangle to measurements that are going to help us find this relationship here. And in fact, using this, I can express side 1 in terms of things in a triangle. So like if I multiply by 11, I can say that side 1 is 11x over the square root of 377. I could write it like that too, but this is just more succinct. Now if I can write side 2 somehow in terms of x also, that would be great. It's going to be a little bit more challenging. I guess we have to do one other sort of thing, but thinking same sorts of relationships and somehow involving side 2, which is a hypotenuse of this slightly larger but not overall largest triangle. Let's see, if I want to express side number 2, side 2 is related to my hypotenuse, 377, in the same way that, well, I need to relate one other pair of sides off of here, and preferably I'd like to somehow involve an x. Now, this 16 isn't from this point here, it's all the way from A to B, but it's related to the length of this side here, which I can express then in terms of x. Side 2 is the hypotenuse. It relates to, oh wait, did I write the wrong thing? I did. I was thinking about 11 and I wrote it. Side 2 is related to this hypotenuse, square root of 377. In the same way that, well, this side here, from this vertical line that I've just drawn to there, 16 is the whole thing. If this part's x, then the remaining part here is going to be, 16 minus x. So I can think about this side length here related to the whole corresponding bottom side. So this triangle that shares angle B with our right triangles in the same orientation as the whole ABC, their hypotenuses are parallel. Its base that has an angle A equivalent is right on top of triangle ABC's base, AB. So 16 over x, the part of this smaller triangle, 16 over x, or 16 minus x, is related to this full bottom side, which is 16. Or I can say that side 2 is just multiplying by that radical expression, 16 minus x times root 377 all over 16. And now we have an expression for side 1 and side 2 that both involve a single mystery variable x. Now your book talks about this whole imagine a fixed shape. If I have this expression where I represent x, like imagine x is this big, well, I could change the size of x as long as it doesn't go below 0 or past 16, and this would still be okay. Might run into some other problems if you're at 0 or 16. But if I imagine it being something in the middle, I can maybe put together a picture, but in reality what we're doing is we're letting x vary and figuring out which value of x gives us the largest S1 times S2 result. And since we have expressions for both of these, now we can do that. So if I write my area as a function of x now, side 1, 11x over that square root, times side 2, length times width, 16 minus x over 16, all times this root 377, wherever you want to put that in. There's just a lot of things that cancel out. So this 370, well, not a lot of things, but the messy things. Multiplying two fractions, they're in factored form. I can cancel out that length of the hypotenuse nicely. So if you look at what's left, we've got 11x times this binomial all over 16, or this could be more simply written as the area in terms of x. I'm going to write a coefficient 11/16 times x times 16 minus x. And this is really the hard work of the problem, putting together all the pieces of information and being able to write a function that has just one independent variable, but contains all the rules and regulations of the problem. In this case, the fact that I've got one geometric shape inscribed in another, there's all these similar triangle relationships and Pythagorean theorem relationships that we needed to use. But by the time we've gotten this all written out and just do minor simplification, notice that this function we're trying to maximize in this case, is just a quadratic function. So that's something you actually learned how to do, that aspect of it, probably in an algebra class. Find the vertex of the parabola. This is a parabola with a negative 11/16 x squared leading term. So it opens down. We can find the vertex. You can use algebra, like negative b over 2a. You could use calculus, multiply it out maybe, find the derivative, figure out when it's 0, or if you remember anything about parabolas and their symmetry, this is vertex form. This one has x-intercepts at 0 and 16, so guess where the vertex is? It's at 8. So there's a variety of ways you can get to this, but x equals 8 will maximize the area. Now, that isn't the answer to the question, because the question didn't say anything about x. Maximizes area. But if I wanted to answer the question here, now I've got all the ingredients. I need to make this x equal 8, or in other words, put that vertex of the rectangle smack dab in the middle of the base of the triangle. But since I wrote out all these relationships earlier, I know how to find the area, A. I can use this area function right here. But if you want to go back to this original form, the question actually asks what dimension should the rectangle have. So that would be what would be the length and width. So I need to write out the values of side 1 and side 2, their lengths. So it does involve that square root of 377. It is important. It doesn't entirely go away. Just that in the function, after they've been multiplied together, the two dimensions, it does disappear. So in this case, 11 times 8 over the square root of 377 would be the length of this side, and 11 times, or not 11 times 8, 8 times the square root of 377 over 16, in other words, 377 over 2, is the length of this other side, root 377 over 2. Sorry, I keep forgetting to say the square root part of that. So whatever on earth that comes out to, it comes out to unpleasant decimals or like the radical form. But the bulk of the work in these questions is getting to this point. Because after that, you can say, oh, well, once I get the function written, then it's just bing, bang, bong, done. I've got an answer using some symmetry or something, and even if I use calculus, it'd be a pretty simple answer to get using, like product rule even, get fancy, don't multiply it out. It's still fairly easy compared to all of the rest of the preceding work. So when you're encountering these problems, which are in, I believe it's homework 17 and 18, or maybe 16 and 17, there's a bunch of these optimization questions. Don't be in a rush to write a formula down and just start taking derivatives. Take your time. Draw a picture if that's something that helps with the problem, if it's something visual or geometric. Label some dimensions if you have something like that. Think about the relationships between the quantities that you have, the rules and regulations, the constraints that are put on the lengths of the things you have. Now in this case, I didn't talk about it too much other than just say, well, x has to be something between 0 and 16. Okay, but that didn't come up to be an issue because the only critical value that we'd have from this would be at x equals 8 anyway, which is between 0 and 16. And that is the maximum value of, if I were graphing function a of x, capital A, it would look like this. And at 8, that's where the vertex is. And I don't know what the area is. It's unpleasant things multiplied together, but I can get it from this. 64 over 16, that actually should not be too hard. 44 square units, whatever units we were in, inches. So in any case, like I said, there's a lot of different relationships. So I want to do this problem because it brings up a lot of random geometry that you might not have thought about in a while. Similar triangles and perpendicular lines and 180 degrees in a triangle and Pythagorean theorem, and there's just a lot of things. So I want to show you another question that's in the homework section of this, which is somewhat similar to a homework problem in iMathAS. Not exactly the same as, but it is, let's see, this one. So I'm going to move this guy out of the way for a minute. But this is drawn at an angle as opposed to looking straight down on the river. But station A and B are across the river from one another. We need to lay cables to connect the relay stations, fiber optic cables, and going underwater across the river or over the water, however you're going to do this. It's more expensive than going along land. So we'd like to keep that to be, not too much across the water. But in the same hand, if you don't take the shortest distance between 2 points straight line and instead go around the sides of it, you're going to end up with more cable, so more cost for that reason. So this situation is, if I were to draw this in a less offset manner here than what's here, and I'll get this out of the way. I've got a river, and I've got something here and something there, and I'm trying to get between the two of them. And so I could go, let me change colors here. I could go, maybe straight across this way and then straight across that way, all on the land and then across the water. Or I could kind of go part and part. Obviously, if I go straight across the water, then across, that'd be the same. But maybe I go partially across land and then partially across the water. And our goal is to figure out which of those is cheaper, given the fact that the distances are listed here. The distances, like left to right in this picture between the two stations, are 1,400 meters. The river is 650 meters across. The cost to lay the fiber optic cable just on the land is $75 a meter, and when you're dealing with going over or under the water, because it doesn't really say, it's $125 a meter. So I'd like to give you a little bit of time to think about this question and work on setting it up without my input to start, other than what I've already said. Maybe talk with people around you, but take a little bit of time. And oh, that all went away. Well. going to draw my own diagram on a blank sheet, so that there's space to do work here. 1400, 650. So the question actually asks you to try to find the best way to do this, and then asks you whether it's, to show that it's cheaper than if you were to go all the way down along land and then just straight across the river. But when you're looking at these problems, sometimes just in terms of setting up the problem, looking at an easier case or a simplified example of how it could be set up will help you think about how you can set up your problem in general. So again, our goal was to figure out how to minimize our cost. So if I was doing it this easy way, where I know the two lengths that I'd be using, the cost would be, well, let's see, it's 1,400 along land, or 1,400 meters along land at $75 per meter. And then a separate section, 650 meters underwater. I drew it, looks like part of it's on land, but just 650 meters underwater at $125 a meter. So 650 times 125. And so this is just the, like, kind of an end case. Like, this is the most land and the least water I could do. I could do all water, just diagonal all the way across, but that clearly wouldn't minimize the cost. Maybe because thinking, well, if water's more expensive than land, I don't want to do all water. But it is shorter, so it really kind of depends on how things work out. And it's not just the distances that matter, it's also the relative costs of the two that do affect how it's going to be cheapest. So for instance, if it's 5 times more expensive to go underwater, I guarantee you this is going to be the cheapest way to build this. But it's not 5 times as much, it's like 1 2/3 times as much to complete a meter of fiber optic cable underwater as compared to on land. So it's a little bit more, but not an extreme amount more. So if I wanted to think about this in general, not going all 1,400 meters on land and then just straight across 650 meters, but if I go some on land and the rest, well, across the water, I can still have my nice right triangle, thinking about last problem. Some of this question is very similar to the last question in that regard. 2 things. One, there's a Pythagorean theorem that we're going to need, and also, well, I've got this length of 1,400 meters that I want to be able to express both pieces of it, even though I don't know how long either piece is. But let's say I want to go along land for some certain length. Like if it was 200 meters here, then, oh, this would be 1,200. And then this length is 650, and I can find the length of the hypotenuse. If this is 800, then this is 600. And then this is still 650, and I can find the length of the hypotenuse. So if you know one of these lengths, then you know the other one by subtracting, and you can find the hypotenuse from Pythagorean theorem, and thus find the other length that you needed. But for making Pythagorean theorem pieces easier, let me call this section x. You don't have to. But let's say that that is our x, mystery unknown. This is 650. It's not unknown or variable. But this could be different lengths. Oops, sorry. This could be different lengths here. And depending on how long x is, this part's also going to be different lengths. And they add up to a total of 1400. So I'm going to call this part 1400 minus x. You can do it the other way around also. But why I did it this way is for making Pythagorean theorem expressions less unpleasant, because it's only going to have x squared involved in it, not 1400 minus x quantity squared. Just from, I have looked at this sort of expression before, so I picked it that way. But you don't have to. There's a variety of different ways you can set this up. You can also use trig to do this, which we'll do a trig example, trig review, and then an example next. But if I want to express my cost, I need to express each distance that I'm laying cable for. So 1400 minus x is going to be at the $75 a meter. And oh, this length here, don't quite have it written out, but pretty close. It'd be the square root, the length would be square root of 650 squared plus x squared, Pythagorean theorem wise, and that length would be at a cost of $125 per meter. So if I want to write overall an expression for this, let me go back to cost. Cost I can write as a function of x, where I know this is just $75 a meter. So similar to that, but just with a minus x. So 1400 minus x times 75 plus, from the second part, the length of cable isn't 650 anymore. It's this hypotenuse, square root of 650 squared plus x squared. Times the cost for lying cable under the water, which is $125 per meter. So this would be a cost in dollars based on a variety of different values for x. You could pick a value for x and see how this comes out. You could check a few numbers and see where it seems like what might be the best value for x. This one isn't going to be as easy to solve from here on out as the last one, but at this point we have that function written down whose dependent quantity is what we're trying to, in this case, minimize, cost. So the only other thing we might want to think about is domain here. We didn't really talk about it last time because it was a simpler expression, but x needs to be something between 0 and 1400. If it comes out otherwise, well, then we're not going to use it. X could be 0, in which case we'd have this situation. X is 0, then that first part's just 1400. X could be 1400, in which case it'd be the all underwater situation. And anything in between is going to be a mixture. So if we find this critical value between x equals 0 and 1400, and it's the sort of critical value where the derivative changes from positive to negative, we've got a maximum. If it changes from negative to positive, which is what we want, we'd have a minimum. So taking a look at this function, it's not an obvious, like, what does this look like? This isn't a parabola. I've got a square root of a quadratic and a linear term. So the linear term's derivative is going to be maybe easier to work out the derivative. But our objective function, so there's a couple of words I've thrown around here, which I don't know to what extent they're used in the book. But this function who we're trying to maximize or minimize, who, that, whatever kind of pronoun I want to use. It's not really a person. This is called an objective function. Our goal is to do something with this. And we've worked out its domain. When we have some other relationships or rules and regulations that we have to follow, like that are sometimes are given as equations, they're typically called constraints. In the examples that we talked about last week, I forget if it was Tuesday or Thursday, find the maximum value of 2a squared plus b squared, where a plus b equals 25. Like, oh, a plus b equals 25 is a constraint equation. Rules like that that are written as equations are typically called constraints. Sometimes we don't end up writing them down independently. It's just a part of our generating this objective function. But if you do see something and it's referred to as a constraint, it's just like a limitation or why I can't just pick x and y are both infinity. It has to do with limiting our domain or using only specific values in combination with one another. So I want to know where this has critical values. So the endpoints of the domain, 0 and 1400. I don't know why this keeps looking like. And then any values within the domain where the derivatives 0 are undefined. So well, let's take a look at it. It's got the square root of a quadratic. It could have some undefined spots. But if I look at c prime of x, this first expression is just linear. I could multiply it out, kind of say, okay, so big number times big number is a number. Derivative is 0. 75 times negative x is negative 75x. Oh, derivative is negative 75. And then just go onward from there. You could do product rule or something else, but we don't need to. This one here, you can also think, oh, that's just a numerical coefficient on this square root function. If I want to find the derivative, I'm just going to copy down the coefficient, 125, even though it's written at the end, constant multiple, times the derivative of this. This looks kind of like the medium level of difficulty mastery problems, finding a derivative using chain rule here and the square root and quadratic functions. But derivative of exterior function, a square root function, says we're going to have 1 over 2 times this exact same square root, whatever 650 squared is, plus x squared, times the derivative of the interior function here, which would just be 2x. So mastery test-wise, we say, leave it like that, we're done. End of the question. Now, oh, and I don't know where this came in to be a plus. That was supposed to be a multiplication. This is our coefficient constant multiple. Sorry about that. So looking at this, so I've got this is the derivative of that first term. Here's the derivative of the second term, the underwater part, much messier. But we can simplify pieces of this, which will make our life easier, because now this isn't end result. This isn't just show me the rate of change function. This is, I want to know when this is 0. So if you can do some simplifying, please do. Like for instance, those 2's, there's not a lot of stuff that can simplify here, but those 2's can certainly go away. And then I've got a constant term and this 120 and an x multiplied onto this. I'm going to clean this up a little bit and say that our derivative, c prime of x, I'm just going to put this minus 75 at the end, would equal, let's see, 125x over that square root, and then minus 75. .650 squared plus x squared minus 75. So, like I said, for derivative finding purposes, no need to simplify that. But for the purposes of doing anything with derivatives, it's a lot easier. I can't move this. Sorry. Now it's going to be all gone. Let me just rewrite that quickly. Sorry, this thing is misbehaving. Ugh. For derivative finding purposes, or derivative finding equal to 0 purposes, let's see if I can remember what I had here. 125x over that square root, 650 squared plus x squared, all minus 75. So that was our derivative. I want to know when this is 0 or undefined, as well as my endpoints. Remember, x was only supposed to be in the interval 0 through 1400. So if we do find a value of x and it's like 1600, then we're not going to use it. Even if it is minimum, it's not allowed. It'd probably be maximum if it's out there. So I want to know when this equals 0. So From here, it's really just algebra, but I do want to go through it. So in terms of like, how do you find this algebraically as opposed to just estimating graph on a calculator or something? I want to know when this is undefined. That would be a derivative or a denominator equal to 0, which that's not going to happen because I've got a square root of positive number plus a positive number. Well, 0, bigger number. That's going to be okay. It's not going to be a square root of 0 or a square root of a negative, either one, based on the expression underneath. So I don't have to worry about this derivative being undefined. So all I have to, the only sort of critical value I could have then is a place where this is 0. So just quick algebra stuff here. 125x over the square root minus 75 equals 0 is going to be the same as equals 75. Multiply across your denominator, so it's out of the way. And that's a 650 squared. And then at this point, we've got x on both sides, but we needed to get it out of the denominator. So this is when you get to square both sides. So I don't know what 125 squared is. I'll write it that way. If I square the right-hand side, I get 75 squared, and this stuff without the radical sign, which still has squares in it. But square root, when the stuff underneath is positive like it is, you get the stuff underneath. So I've got this lovely expression, which I don't want to finish up all of the algebra here from here because it's just a lot of large numbers, but you can see that, oh, it's just a quadratic expression. In fact, it's a quadratic with only quadratic and constant terms. There's no linear x's also. So although there's huge coefficients, 75 squared and 125 squared, whatever on earth those are together, let's see if I can write this, 125 squared and 75 squared are the coefficients on x squared. And this other side would be 75 squared times 650 squared. I get to divide and take a square root. So guess what? All those squareds go away. So x squared would be this 75 and 650 and that 125. Oh, no, that's a plus on the bottom. Plus 75 squared. So x is going to be a square root of all that stuff. And I don't know what it is off the top of my head. The numerator can be simplified, the denominator not so much. But whatever this comes out to, I promise you, without grabbing a calculator right now, this is something between 0 and 1400 in this case. It's not a random trick problem. It does come out as it explains in the books, like, why does this value come out to be less than if you went all the way down land and then straight across the water? It is actually less than all the way down land and straight across the water. This, keep in mind, is the value for x that causes that. This is not the cost. This is not what causes a maximum cost either. It is actually a minimum cost. And maybe you can see from this that this derivative, when x is between 0 and 1400, this is all going to be something positive, minus 75. If this part's big enough, it's going to be greater than 75, and it doesn't get big enough until x passes this number, which makes this first part greater than the 75 that's subtracted. Yeah? Let's see. Oh, so where that came from? Let's see. Oh, yes, it should be. Sorry. Yeah, so what I missed here, I was moving stuff across the equal sign and simplifying at the same time, but this is actually a minus. But in any case, it's not a trick question, but again, this idea of measuring lengths using one variable, 1600, instead of dividing it into like x and y, it's x and 1600 minus x, or whatever your numbers are. I think 16 was from the previous problem and 1400 from this. There's one other type of problem involving these sorts of measurements and assigning values to them that I want us to go through, but there's a bit of trig involved. So let's do a quick trig review first, just briefly. And then I want to show you the problem. I'll post it in Canvas for you to look at between now and Thursday, and then we'll talk about how to finish up that problem in class on Thursday. So other problem is not on here. I'm looking for this guy. All right. So trigonometry, the word comes from related to triangles, but it was extended to apply also to circles, or just generally what trigonometry does. It relates angles and lengths. So those lengths can be lengths of a side of a geometric, like straight-sided shape, or it can be measurements within a shape, or it can actually also be used in conjunction with or in relationship to measuring arcs of circles that contain the same angles. So radians are the standard unit for measuring angles when you're in circles. If you're just dealing with triangles, you'll see radians and degrees both. But for the purposes of calculator usage, if you need to find things, just realize that they're in radians by default. And lots of times with sine and cosine functions, those are assumed to be using like y equals sine of x, y equals cosine of x. The x there is assumed to be an angle measured in radians. So that said, radians are based on radius length of a circle. So a circle in degrees is 360 degrees all the way around. In radians, it's how many radius lengths fit around the edge of it. So a radian of a circle, 1 radian is about that long in this circle, but it pertains to, it's the length of 1 radius of that circle extended outward. You can see it goes part of the way around the circle, about 1/6 of the way around, in fact. And so if you go all the way around a circle, I just passed the end. It's 2 pi radians, because the formula that you know for circumference of a circle is circumference is 2 pi r, where r is the radius length. So a radius length of a circle would fit around the outside of it 6 and a little bit, 6 and 6.28 times approximately. This just shows the 2 decimal places of accuracy, if you know from our slider stuff. But in any case, these numbers here, they don't have to be nice round multiples of pi. Like here's 1.99 radians. What that means is this ray that forms this central angle in the circle, and we start in the first quadrant, go around the quadrants in order. First, second, third, fourth is the standard order for measuring angles. So acute angles are in this first quadrant in terms of where their terminal angle side is. Something like this, where it's less than 90 degrees, thinking degree-wise, is in this first quadrant. And you can see that by the time I get to right around the top here, I'm right around 1.5 radians, or 1.5 radius lengths to go through one quadrant. I can go to 2, I can stop at any number that I want. And what this is my number of radius lengths. So I'm at 2.89 radius lengths, puts me into the second quadrant, is referring to this obtuse angle here, whose arc subtended by it is out here. So this arc length can be measured in terms of the angle here. You can also measure the distances in various locations based on the size of this angle, but it's not, I have this circle of radius 1, which is called a unit circle. It doesn't actually matter the size of the circle that we're talking about. Let me put this back to 1. There we go. So I have some other circles here too. My ray isn't long enough. But the radius lengths of these other circles, so the radius of this circle with radius 4, when it lies down on the circle, is the same, like kind of part way through the first quadrant. And on the larger circle with radius 6, again, 1 radius length is still part way through the first quadrant. So 1 radian in angle measure, the central angle of the circle, is irrespective of the size of the circle. But that's why I'll just pick to use this circle with radius 1, because it's A, convenient, B, I don't know, nice round number. So in terms of your trig relationships, your trigonometric relationships relate lengths and angles, and you can see all of that you want in a circle, although you can also use them in triangles if you've got acute angles that we're referring to. Let me scoot this down a little bit. Where do I have that? There we go. So right now I've got an angle that's 1 radian. So generally notation for the angle you typically see in like trig books, is use a symbol theta for the angle, but you can use whatever you want. Let me call this angle theta. So depending on the size of this angle, which right now is 1, it's 1 radian, meaning 1 radius length, but that's the length of the arc. Let's see, do I have anything closer? Here. This arc's length depends on the radius of the circle, obviously, more so than the angle doesn't, but this arc's length is the radius times the size of the angle. So the radius of this circle is 1, the size of the angle is 1. So if this radius is 1 inch, let's say, then the arc length is also 1 inch. So if I have this is like dragging. If I have a larger angle or a different angle, whatever, whether it's larger or smaller, then I can have larger arc lengths that go with it. So this is a 2.49 radius or radian angle now. That means that this length here is 2.49 inches, since this is a 1 inch radius. If it was the larger circle with a 4 inch radius, this would be 4 times that. It just scales up similar circles, I guess you'd say. But it's the same angle making different size arcs outside it. Now, the triangle part, let me go back to this. So in a triangle that can be formed with these two measurements, thinking about how do I get from the center of the circle to the point where the ray meets the edge of the circle, in terms of horizontal and vertical distance when we're talking about x and y coordinates here. So this distance here, I can see this distance is about, I don't know, it looks like 0.54. And this vertical distance looks longer, let's say it's about 0.85. Just eyeballing how long these sides are using the coordinate grid. So these two lengths obviously are related to the angle. We talked about the hypotenuse, Pythagorean theorem sorts of things. But if I change this angle, that's going to change the relationships, just like changing the side lengths was. If I make this side longer, then this side has to be in a different spot, makes a longer hypotenuse, and so forth. But if I keep the hypotenuse the same length all the time, which in this case is going to be 1, since that's the size circle I'm in, these segments here, I can refer to these by sine and cosine functions. So the sine function of an angle, any angle, triangle-wise, so thinking about like right triangle trigonometry, sine is opposite over hypotenuse, right? And the extension of that into circles is that, well, if I'm looking at this, I've got a hypotenuse of 1 here. In a unit circle, which is what we've got here, I can also see that this would be the same as this vertical length, or the y-coordinate of this point. So this point would be about 0.54, comma 0.85. So the sine of this angle would be that vertical distance, or the y-coordinate of the point on the edge of the circle, divided by the radius of the circle. Or if the radius is 1, that's just y. In general, I could describe the y-coordinates of this circle as being the radius length times the sine of angle theta. Or I could solve and get theta equals arc sine of y over r. But sine, based on, it was designed in terms of triangles. So the sine function relates the opposite length from the central angle in a circle to the side opposite in this triangle that's made there, but it was originally made for triangles. The thing is, we can extend it to refer to things that don't fit in right triangles. Any angle 90 degrees or larger still has a sine value, but it's based on this alternate configuration, or this other way of defining the sine function, so we can extend this to any rotational angle as opposed to just things that fit in triangles. So we can think about this as theta increases, or think about something that's spinning over and over or goes through a variety of values. Cosine, likewise, is related to this blue part here. So cosine in triangle formulations is adjacent over hypotenuse. Adjacent side to the angle in the right triangle that isn't the hypotenuse, and then the hypotenuse itself. So extended into triangle formulations, here I can see, oh, adjacent would be this 0.54, or the way that we set up angles, it's always going to be that along the x-axis length, or the left to right distance from the center of the circle of rotation, the center of rotation, wherever you want to call this. So in a circle, I can define that as, well, whatever this x-coordinate length is, divided by the radius, which is 1 in this particular circle, but it could be something else in a different one. Or I could say that that x length, or the x-coordinate where I intersect the circle, is dependent on the radius of the circle and the cosine of the angle. So again, there's the triangle formulation, and then how we can extend that to circles. But what that means in circles is that trig values can come out negative, because we can have negative x and y values, and they just relate to all the different quadrants of this, and you probably learned about reference angles at some various points in time in your past. But it's just talking about these distances, but in different orientations to the center of the rotation or to the center of the angles that are being formed. So there's a lot of details of trig, and we're not going to review all of trig, but I just wanted to make sure you generally understand the visual relationship between sine and cosine, which are going to be the most useful for us most of the time, and angles. So if you need to talk about how do I arrange this angle to maximize something, or if an angle is going to help you compute something, think about sine or cosine, and you can generally pick either one that you want, because one is just as easy to work with as the other. Possibly tangent, which would involve not needing to worry about the hypotenuse at all. But generally, if you can find one trig function value, you can find all of the others from that. So typically, we just need to pick one and stick with it, and you can get through these problems. Some make it easier than others to set up equations. But in terms of these relative lengths, they're all related to relating the angles with trig functions to these lengths left, right, up, and down from the center that these points on circles maintain. So let me clear some of this off. So if I have a different angle, something like this. This is a 5.18 radian angle. If I want to describe the sine of 5.18, it would be the, well, length per se of this red line, but in reality it's the y value at the end of this red line segment, which is almost -1. So maybe -0.95. So if you were to grab a calculator and check what's the sine of 5.18, it should be -0.9 something. It is just referring to these distances, but distances with signs to indicate the direction. So left, right, and up, down, just like on the coordinate axes, which we are on. So you can estimate visually if you have something like this, but typically we're not actually looking for you to try to evaluate using a decimal, find the sine value of something or another. And I'm not going to make you remember like √3/2 is the cosine of something. Just keep in mind the relationships that are involved in sine and cosine, and tangent, also useful. Tangent is sine over cosine, or otherwise known in triangles as opposite over adjacent, or in circles as y over r, or y over x. So let's take a look at one last question, and this is going to be, I want to talk a little bit about it now, and then we'll go through it the rest of the way over the weekend. But, all right, let me make the text to this bigger. This is a document that I'm going to post. But in the middle of an upcoming race, so like some sort of Spartan race or something, there's a big pond obstacle. And competitors will approach the pond. It's a circular pond with a radius of 1.8 kilometers that's directly between the person and the finish line. And they can choose to run around it, although it's a rocky beach beach and they have to stay down on it, so they're not going to be able to run fast, or they can swim through it, or they can do a combination of both. So here's the picture. I'll get back to the details. So just as an example, maybe to do something like this, approaching, run part way around the edge and then swim because it's treacherous and you don't want to swim and then try to run. But you can run and swim at differing speeds. So if somebody running this race knows about the obstacles in advance, they're not going to do this while they're racing the earlier parts of the race and just mentally calculating. But if you know about this obstacle in advance and you know from trying it out that you can run along the rough terrain at the shore at 4 kilometers per hour or swim through it at 3 kilometers per hour, we want to figure out how to win the race, how to get through past this obstacle as fast as possible. So use the least amount of time, in other words. Right? So we're trying to minimize the amount of time required to get past this. So some things to think about here. So this was in the top paragraph there, but the radius of this is 1.8 kilometers. And although there's not a right triangle when I just connected that there, I can think about angles. I'm going to call this theta. And I can make a right triangle. And in fact, kind of related to the triangles we were drawing earlier, I can make a right triangle that includes another right triangle. And so various pieces of this might be useful for various computations needed. But if you can see, I've got, by setting up this angle theta here, I've got running along this arc here. And we can do that at, Aaron, can do this at 4 kilometers per hour. I would like to know its distance, because if I know a distance and a rate, I should be able to find the time required, because we're going to try to get by this as quickly as possible. So something about this, I should be able to figure out how long it's going to take her to run this. And if you're not quite sure how to set it up, pretend you have an angle of, I don't know, like 1 radian, because it looks kind of like the diagram that we were looking at. Suppose that's 1 radian. If that's 1 radian, how long is the arc? How long would it take her to run it? And then how would you do that in general if it's not 1 radian, if it's theta radians? How could you express the time required to complete that running? And then there's the swimming, which I've got a right triangle here. Don't really know that length. This length is more than 1.8 because it's more than the radius, but you might remember how long this is, at least in terms of theta. So I want to leave it at that. A couple of helpful hints there maybe to get you started on this, but take a look at how you could write an expression for the time it takes her to get past this obstacle in terms of theta. Theta would probably be a good one. And if you were able to get that, see if you can figure out how on earth to solve it. It's kind of unpleasant. It does involve some trigonometry. But if you get the function written as a function for time in terms of 1 input variable, GC can help you. You can graph it. You can find minimums, visually speaking. And think about the domain as well. All right, so I'll stop that for today. I will see you on Thursday. We'll continue talking about this situation.